Hi, John Spray here. If the holy grail of rocket engineering is full and rapid reusability, then what's the holy grail for software engineering? Zero coupling. Zero coupling, the ability to read and understand any one piece of the software in isolation without also having to read and understand any other part. No design time collaboration, either explicit or implicit, between parts. In this paper titled Building Maintainable Software Using Abstraction Layering, we lay out how to achieve this goal. In section 1 of the paper, we introduce a study of two versions of software which have the same functionality. One is a legacy application, around 70,000 lines of code, going back for some 20 years of maintenance. The other was a rewrite done by intern students, trained to use a new architecture called Abstraction Layered Architecture, which we will refer to as ALA. The purpose of the study was to compare and measure the maintainability of the two versions. Section 2 of the paper explains what ALA is. Fundamentally, it consists of three constraints. Constraint 1, the only unit of code is an abstraction. Constraint 2, only one type of relationship is allowed, a dependency on an abstraction that is significantly more abstract than the one using it. Constraint 3, all abstractions must be small, so of the order of 100 to 500 lines of code. These three constraints give rise to many emergent properties and qualities, some of which we will discuss in the following slides. Abstractions are qualitatively different from modules, components, or classes. An abstraction must be a conceptual idea. The conceptual idea makes it stable and learnable. It becomes part of your language. The internal code of abstractions is zero coupled with one another. Dependencies are only on the conceptual idea of an abstraction, and so introduce no coupling. For example, when the abstraction standard deviation uses the abstraction square root, for the purposes of understanding the standard deviation code, it is only a dependency on the concept of square root. There is no coupling between the standard deviation code and the square root code, and vice versa. So, rather than loose coupling and high cohesion, ALA is said to have zero coupling and high cohesion. Coupling occurs in conventional code mostly because we have a habit of using design time dependencies to implement runtime communications between peer modules. This causes modules to have a fixed arrangement and then to collaborate with one another. ALA replaces coupling or collaboration between modules in conventional code with explicit and cohesive code completely contained inside a new abstraction in a higher layer. When you zoom inside an abstraction, there is no internal structure imposed by ALA. There is no analog of a submodule or subcomponent, no such thing as a sub-abstraction. Instead, you compose using abstractions from lower layers, which must be more abstract and of course more public so they are reusable. The code inside an abstraction is highly cohesive, a small ball of mud, so to speak, which is why small size is one of the fundamental constraints. The ALA constraints cause the emergence of discrete abstraction layers. Abstractions in each layer tend to have certain characteristics, so we name the layers by these characteristics. Application or user stories layer, domain abstractions layer, programming paradigms layer, ALA foundation layer. Each layer is given its own subfolder in the solution. We call the dependencies knowledge dependencies because you need knowledge of the ideas represented by the abstractions in lower layers to understand code in higher layers. If you don't need the knowledge, then it's a bad dependency and illegal in ALA. As you go down the layers, the abstractions have increasing abstractness, reuse, stability, and learnability. This is the wiring pattern. It is frequently used to build ALA applications. Abstraction D at the bottom is a programming paradigm representing a compositional idea, such as UI layout or data flow. D is implemented as an interface. B and C are two domain abstractions implemented as classes with ports. In B, the port is a field of the type interface D. In C, the port is the implementation of interface D. The application abstraction A can wire an instance of B to an instance of C because they have compatible ports using the programming paradigm D. Wiring causes the instance of C to be assigned to the field in the instance of B. So the pattern is a dependency injection pattern, with the injection directed by the explicit code in the application layer. The instance of B and the instance of C can now communicate at runtime, even though abstraction B and abstraction C know nothing about each other. The wire-to method is defined in the foundation layer as an extension method for all domain abstractions. Programming paradigms like D provide the meaning of composition. ALA uses the principle of compositionality. The meaning of a complex expression is determined by the meanings of its constituent expressions, the domain abstractions, and the rules used to combine them, the programming paradigms. The implementation of a programming paradigm can be extremely simple. Note the abstractness level of the interface. It's just the concept of data flow. In conventional code, even if dependency injection is used, there are still dependencies directly on the methods of a peer class or an interface that is essentially owned by the peer classes. These dependencies are illegal in ALA. Interfaces must be one level more abstract, like this one. This is a diagram from inside an application abstraction in the top layer. It is a small part of the full application that was studied. The application layer is an explicit and cohesive expression of the requirements. All details from the requirements are represented here. The boxes are instances of domain abstractions. The lines are wirings between their ports using the wiring pattern described earlier. The diagram uses several different programming paradigms. Note the user story for exiting the application. The instance of main window on the left contains an instance of horizontal layout abstraction called menu bar, which contains a file menu, which contains a menu item labeled exit. All these instances are wired using a UI layout programming paradigm, which is used to build the UI. When exit is clicked, it outputs an event using an event-driven programming paradigm. That output is wired to the close port of the main window. This diagram is executable. We'll return to it in a minute, but first let's execute it. We translate the diagram into code that looks like this. The new keywords instantiate domain abstractions, and the wire-to operator is used to wire them together exactly as directed by the diagram. You can see this code as part of the diagram that implemented the framework of the UI and completes the previously mentioned exit user story. Here is the diagram executing. In user story 1, it waits to sense a device on the serial COM port. When one is connected, the status line changes to connected in green. It automatically loads the session list, which is like a file list, from the device and displays them on a grid. In user story 2, you can select the rows on the grid. This will cause data to be loaded from the device and displayed on another grid. Different sessions can have different data columns. In user story 3, we can use the file menu, then the import from device menu, which causes a wizard to open. Selecting local CSV file causes a save file browser to open, and after selecting a disk file, data is transferred from the device to a CSV file. Back to the diagram. It implements all those user stories. Let's see how the diagram implements user story 3. The file menu near the top of the diagram contains a menu item, import from device. When import from device is clicked, it sends out an event which is wired to an instance of a wizard. This causes the wizard to open. The wizard UI contains wizard items, one of which is local CSV file. When selected, the wizard item outputs an event, which is wired to an instance of Save File Browser. The Save File Browser in due course outputs a file path, which is wired to an instance of CSV File Reader Writer. This is using the data flow programming paradigm. The file path also goes to an instance of ToEvent, which turns it into an event, which is wired to an instance of a transfer abstraction and starts the transfer. Transfer knows how to pull batches of tabular data from its input and push it to its output. This is using a tabular data flow programming paradigm. The input is wired to an instance of SCP data. The SCP data abstraction knows the commands to use for the serial devices to input data. It is wired to an SCP protocol, which knows how to use the general serial protocol used for devices. It is connected to the COM port abstraction using a two-way character data flow. The output of transfer is wired to the CSV file reader writer. Here the programming paradigm is tabular data flow again. CSV file reader writer knows how to write the data as a CSV file, complete with headers that also come in the tabular data flow. Note that we were able to read the entire code for the user story in one place, and it only took a minute. In the legacy code, the user story involves collaboration between a lot of classes, and it takes about a day to trace and read that code. The coupling or collaboration in the legacy code has turned into cohesion in the ALA code. The user story was just a composition of domain abstractions and polyglot programming paradigm. The domain abstractions, together with the programming paradigms, constitute a domain-specific language for expressing requirements. Section 3 of the paper is a short section covering the long-term maintenance process of ALA. The flowchart shows that if appropriate programming paradigms and domain abstractions already exist to express a new requirement, then you only have to compose instances of domain abstractions and then validate it. Only the application layer takes the additional code. The graph shows the trend of commits per month to the application layer as a percentage of the total. This was tracked as the application was rewritten by the intern students. As the set of domain abstractions and programming paradigms matures, the percentage of commits to the application layer trends upwards. After 16 months, the application layer was seeing more than 50% of the commits, even though it was only 10% of the code. In section 4 of the paper, a systematic literature review was done to identify metrics for the 5 sub-characteristics of maintainability in the ISO 25023 standard. The figure shows the metrics used for each of the 5 sub-characteristics. Some metrics, such as CBO, coupling between objects, influence multiple sub-characteristics. We used a tool to generate dependency graphs for the legacy and ALA versions. The legacy one on the left is zoomed in to show the mass of dependencies that had accumulated over years of maintenance. For the ALA one on the right, you can see the layers of the application, domain abstractions, and programming paradigms. It indicates a significant improvement in complexity. The ALA dependency graph would not change much as maintenance continues. ALA distinguishes between good and bad dependencies. Good dependencies are ones on more abstract abstractions. Bad dependencies are used for runtime communications between modules or for splitting modules into more specific submodules. All of the dependencies on the right graph are good dependencies. We actually want more of them because that means we are reusing our abstractions. Some of the dependencies on the graph are probably good dependencies as well, but the majority of them are likely to be what ALA considers bad dependencies. Unfortunately, the CBO metric that was used is unable to distinguish between good and bad dependencies. Summary findings. The modularity, analyzability, testability, and reusability were all higher for the ALA version. For example, the table shows the average instantiated times for classes and interfaces in both versions. The ALA version has several times higher reuse of both classes and interfaces. The modifiability of the ALA version was lower in the beginning, while new domain abstractions are frequently needed for building user stories. But the modifiability improves over time as domain abstractions mature. The total effort to build the two versions is approximately 12 man-years for the legacy version and 3 man-years for the ALA version. The usual experience of developers of conventional code is for modifiability to decrease over time, but for ALA it increases over time. It is said that 90% of commercial software is under maintenance. The metrics indicate that significant cost savings are possible. Thanks for watching.